Hello everybody, my name is Calvin with student ID number of 2205531140. I'm currently studying mechanical engineering in Udayana University. In this video I'm going to present my presentation about polymers. This presentation is made for the assignment of engineering materials knowledge subject lectured by Professor Dr. Tjokorda Tirta Nindhia STMT. All the materials that were used in this presentation were taken directly from this book entitled Science of Engineering and Materials Volume 2 by Menas Chanda. The content that will be discussed in this presentation is cross-linking of polymer chains, stereoisomerism of linear polymers, crystalline and amorphous behavior of polymers. First is cross-linking of polymer chains. Under special conditions, polymer chain molecules can be cross-linked by atoms or groups of atoms that form primary bonds between chains. The cross-linkage may be formed by foreign atoms or molecules. A high degree of cross-linking gives to three-dimensional or space network polymer, in which all polymer chains are linked together to form one giant molecule. Polymers or resins, which are transformed into a cross-linked product and thus takes on a set on heating, are said to be thermosetting type. Quite commonly, these materials are prepared by intent in only partially polymer state or pre-polymers, so that they may be deformed into the heated mold and then hardened by curing or cross-linking. For curing or cross-linking, the resin is mixed with an appropriate hardener and heated. However, with some thermosetting types, the cross-linked or network structure is formed even with little or no application of heat. Next is stereoisomerism of linear polymers. Natural rubber and the majority of synthetic rubber are saturated and possess double bonds along their chain. Unlike the single bond which can rotate, the double bond cannot be rotated. Thus, the center of the polymer is rigid and two distinct structures called isomers exist for the polymer polyisoprene, namely the cheese configuration, which is named for the polymers that groups on the same side, and the trans isomer in which all the olefinic linkages have the trans configuration. In other words, groups on the opposite sides. The new polymers of the general polymer formula, where R is some monovalent side group, have one asymmetric carbon atom marked with the asterisk in each mer. An asymmetric carbon atom is a site of steric isomerism. These polymers may therefore have a limitless variety of ordered structures. Two of such structures are, however, predominantly important and are termed isotactic and syndiotactic. In isotactic configuration, all mers have the same orientation, which can be seen in the figure A. All mer have the same orientation, the R on the upside. Thus, moving along the chain of an isotactic polymer molecule, one would find the substituents R on the asymmetric carbon atoms to be on the same side of the plane containing the zigzag chain of carbon atoms. In contrast, in a syndiotactic polymer, The substituents R would lie alternately above and below the plane of main chain is up, above, below, above, below, alternating. If the target arrangement of the substituents on the asymmetric carbon atom is random or very nearly so, the polymer is said to be atactic, which can be seen on the figure C. It is below, above, below, so there's a random pattern. This is called atactic. This is the crystalline and amorphous behavior of polymers. Although a few polymers may be completely crystalline and a few completely amorphous, most polymers have the characteristics of both crystalline solids and highly viscous liquids. This is also revealed by X-ray and electron diffraction patterns of polymers, which often show the sharp features characteristic of crystalline solids as well as the diffuse features of liquids. Such polymers may be said to be partially crystalline or semi-crystalline in character. The nature of polymer crystallinity has been the subject of considerable controversy. The French missile theory, developed in the 1930s, pictures polymers as consisting of small-sized, ordered regions of local crystallization termed micelles or crystallites, embedded in the unordered amorphous polymer matrix as seen in the figure A on the left of this figure. Polymers are considered to extend through several micelles, where segments of different polymer chains have precisely aligned together to undergo crystallization. The segments of polymer chains in between the micelles are unordered, forming the amorphous matrix. The folded chain lamella theory arose later, when it was shown that polymer single crystal in the form thin platelets, termed lamella, can be grown from polymer solutures. X-ray examination of the single crystals indicates that the polymer chains are perpendicular to the planes of the layers. Since the polymer molecules are longer than the thickness of the single crystal, they evidently fold back and forth on themselves in the process of crystallization, and consequently, the surface of the crystal consists of hairpin turns, as illustrated in the figure B. The hairpin turns, and they are perpendicular to the plane. Polymers, according to this theory, are considered to be one-phase chain folded crystals with varying amounts of defects. These defects may be loose in chain ends, imperfect folds, chain entanglements, dislocations, or other types of imperfections. The extent of which polymer molecules crystallize depends on the structure and on the magnitude of secondary bond forces among the polymer chains. The greater the structural regularity and symmetry of polymer molecule, and the stronger the secondary force, the greater is the tendency toward crystallization. A few examples are given below. Linear polyethylene has essentially the best for chaining packing. Its molecular structure is very simple and perfectly regular, and the small methylene groups fit easily into crystal lattice. Substituents hanging off polymer chains lead to difficulties in packing and generally decrease the tendency towards crystallization. Moreover, crystallization does not take place easily when polymer molecules have a low degree of symmetry. Copolymerization reduces the structural symmetry of a polymer. It is thus a very effective method of decreasing crystallization tendency of a polymer. Chain flexibility is also a factor that affects the crystallizability of a polymer. Excessive polymer in a polymer chain gives rise to difficulty in chain packing, with the result that such polymer remain almost completely in the amorphous state. On the other extreme, excessive rigidity in polymers due to excessive cross-linking also causes inability to crystallize. The presence of polar groups along the polymer chains greatly increases the intermolecular or secondary restriction forces, which is favorable for crystallization. However, high secondary forces alone may not give rise to high crystallinity, unless the chain segments are brought together so that the polar groups are aligned. Such alignment of polymer chains is often facilitated by mechanical stretching of the polymer. The degree of crystallinity of polymeric materials is reduced by the addition of plasticizers. Crystallization in many synthetic resins is not always desirable, because it makes shaping more difficult and reduces the transparency by more closely packing the polymer molecules. For these reasons, plasticizers, which cause partial neutralization of the intermolecular forces of attraction by coming in between polymer molecules and thus harness flexibility and plasticity, are often added to the polymeric mass before shaping. Thank you for listening to my presentation. If there is something wrong about my presentation, feel free to correct my mistakes in the comment section down below. Adios.